Hello.
Yeah, you're live now, GP.
Okay, sounds great. So, so primarily, this isn't actually in the Word format. The reason being is that this is a book that's just about to be released very soon. So I haven't formatted it in a PowerPoint yet for that reason. So we're going to go over today in our session the origins of deep learning, and then we're also going to take a look at linear algebra and calculus as well, and the programming tools in order to compute various calculations, and how we can leverage the math in neural networks. We're gonna have multiple programming languages. So primarily the book consists of TensorFlow, Python, PyTorch, and also R, which is mainly for statistics. So a lot of statistical algorithms are presented in R, and it is coming to the reinforcement learning. I've written it in PyTorch, and coming to the math side of it, like linear algebra and calculus, I've presented it in TensorFlow. And again, for any of the regular machine learning algorithms, so we can take a look at like, k-nearest neighbors, or clustering algorithm, classification algorithms, or naive Bayes algorithms, regression algorithms, a number of other algorithms are presented it in Python. There's also another section for exclusively natural language processing, for processing some large volume text data sets, and how we can leverage and implement that. So that I've covered it in Python as well. So for this particular session today, we're going to go exclusively for linear algebra and calculus, which will be covered in TensorFlow programming language. So before I take a deeper dive into it, I just want to, maybe a little bit of rundown of, what these deep learning neural networks are, how do they work, and how do we do a weight summation, how do we calculate in order to produce an outcome and an output in a particular neural network. So as we have seen that, the neural networks has been on the rise from a decade, and before that, we've been having various architectures for machine learning and deep learning. As we all know that in 1950s, John McCarthy has defined the term artificial intelligence, and parallelly there were some other efforts going on in Britain with Alan Turing revolutionizing or some of the the war that he waged against Germany, and he cracked the code of the cipher, and he came up with Turing machines that laid some foundations for computer science, and how we can actually leverage the math into programming some of the computers and stuff like that. And after that, there are a number of evolutions in terms of the machine learning algorithms, like Bayes neural networks and Bayesian neural networks, and there's also regular machine learning algorithm I just spoke about, all of the classification, regression, clustering, and a number of machine learning algorithms. These were discovered in the 80s, and then further down in 90s, there were a few more architectures that evolved. Even in 80s, like we saw, Boltzmann machines, restricted Boltzmann machines that were invented by Geoffrey Hinton, and then there came autoencoders, and a number of architectures to perform, computations on neural networks. Again, these are all the regular neural networks. So when you're talking about regular neural network, it looks like a simple neural network that probably has only a single layer, and that's all that it performs to compute all the calculations. Then again, a decade ago, we started having these deep learning neural networks, where people started introducing, you can have a neural network with thousands of processing nodes and thousands of layers, hidden layers especially, and that can have millions of neurons. And mostly all of these are feed-forward neural networks, that perform the data connection between the neural traverses in a single direction as well. And so these are all inspired by the human brain. And as we know that there is a brain institute that has funded $1 billion over the years to perform and decode the brain, just like a couple of decades ago we had this genome project where people actually have decoded the human genome. It wasn't possible before that. It took almost a decade to do that because there was so many complications, and plus our processing speeds are not so faster, and the chips that we have are they cannot produce the outcomes in a few minutes. It will take a long time to process the data that we have, and that's why it took almost a decade to that. If you were to do that genome today, I mean, there are a lot of companies that can perform genome analytics in few minutes, or sometimes even in seconds in today's world. And why that is a possibility? Because that's how our processors have accelerated. We are at the verge of breaking the threshold of Moore's law, and advancing processors, and there are a lot of architecture that came up that can train the AI algorithms and increase the processing speeds. I mean, according to Gordon Moore's law, he said, our every couple of years our processors are going to be doubling up, and that's what initially was a trend that was established, which was there till today. And a lot of companies like Intel, Nvidia, and a number of other companies have gone ahead and they tried to process this, and they came up with architectures to go with the 7nm or architectures, which again after that we may have to go for graphene or some other sort of silicon material that we can leverage to actually compute this. So when we do that, then we can get faster results and faster outcomes. So right now, there's still, the GPU is the way to go for it to perform all these computations and get your acceleration of AI training. So as we have taken a look at this particular architecture on this neural network, so we're going to take a look at, so anytime that you have a neural network, so basically each node is connected to the next layer and so on and so forth. And each node is assigned with a weight. And these weights are total, and so by performing a weight summation technique, and as we've seen earlier, so I'm going to show another picture where we can take a look at how the weight summation occurs between multiple nodes. And when we do this weight summation, for each neuron has to be activated as well. And again, there are several ways of activating these neurons. We have a sigmoid function, we have hyperbolic tangent function, and also a lot of times we see the programming languages also come with built-in libraries that deliver some functions that we can leverage. For example, ReLU is an activation function that is already built in a programming language. You can take a look at PyTorch and TensorFlow, you can already find it's built in. And some other programming language you may have to manually apply it. I mean, even PyTorch and TensorFlow can manually apply it, but again, when you do that, when you apply it manually, you will have a lot of issues like vanishing and exploding gradient problems that you will come across. So the best way of going about it is to actually be able to apply built-in functions. But if you do want to apply the sigmoid function, you can do that. This is the formula that you can leverage to perform a linear transformation and activate a neuron, and that is in a hidden layer. And a sigmoid function performs a nonlinear transformation with an activation function. Again, this is a tan or hyperbolic tangent function. This is another type of, again, the hyperbolic tangent function or tan is not entirely different from sigmoid function. It's just a scale function of it. And it will have most of the characteristics that are much similar in nature. It works as a nonlinear function with a range of -1 to 1. And again, if you're going for sigmoid, you have a gradient of 1 and greater than 0. So that's the difference between the two. Otherwise, you can simply scale it up and you can apply this formula and it's going to activate a neuron. And again, as I mentioned above, so here, let's take a look at the input layer. We have Z1, Z2, Z3, and we also have another hidden layer here, C1, C2, C3, C4. And each of them has a weight assigned. So as I said, we can do a weight summation for each node, and then we're going to produce a output neuron, which is C. And so here, the way we do it is we take each particular input neuron, and then we multiply with the particular hidden neuron, and then we're going to produce and we're going to keep on adding them and perform a weight summation for each node. So that will be a total for it. So for example, here, if you look at it, so Z1, Z2, Z3 are our inputs, and then we're going to apply this formula, and then we're going to produce a weight summation here, and then we're going to produce the output. So this vectorized calculation occurs for any of the inputs by stacking the parameters of the neurons in the neural network layer. So now coming to TensorFlow. So TensorFlow is recently mentioned, like it has been there for a decade, but again, mostly was leveraged for any research labs inside Google, and that's how they implemented it. But again, coming back to us, it was outsourced as a commercialization tool where enterprise can actually start leveraging it. That was in 2015. And a lot of companies like scientific laboratories and engineering labs and high performance computing research lab leverage TensorFlow because it's easy to compute the numerical operations, or especially if you're going for multi-algebraic grids or doing like conjugate gradient solvers or fast Fourier transforms. It's much easier to deal with the TensorFlow than any other programming language. And again, PyTorch, of course, is also much capable, and the tensors in PyTorch are also capable of performing all of these operations. And I mean, for this particular session, we can only focus on TensorFlow. And you can run it on TPUs or you can run it on GPUs. And again, you need to wrap up your each module in TensorFlow to be able to do that. In PyTorch, you can just activate your CUDA device where you want to compute this on a GPU or a CPU or a TPU, and then it will simply perform your entire operation in particular, the unit where you would like to execute it. And again, TensorFlow is a purpose-built for numerical computation, and it leverages a lot of data flow graphs and everything you can see in TensorBoard. There is another tool which is like a data visualization tool. So most of the time, if you are writing program in Python, you're going to write to get all of the graphs in Matplotlib or Seaborn. Many of these, data visualization libraries that you have, and you can do all of your data wrangling in Pandas, and you can do your computations of the dimensional arrays in NumPy. Here you can do in TensorFlow n-dimensional arrays, and these are dubbed as tensors, and that's what you can leverage for computation of all of your mathematical calculations. And here are a few other data types that you can deal in TensorFlow, depending on the type of scientific operation you're performing, whether you want to go for a floating point. So vectors are getting obsolete now. So most of the programming languages are switching to floating pointers, which are much accurate and faster in computation. Depends on the type of calculation you're performing. And again, let's take a look at how we can do different types of dimensions of a tensor in TensorFlow. So in TensorFlow, primarily, let's say that we want to measure a quantity of a number or as any particular single value in a tensor, like mass or distance or speed. You can go with a rank 0 tensor, and so you can define that. And so you apply, just to define a string, and you just want to print out. That's what you want to for your demonstration purposes, and go for a tensor number, and assign a tensor variable, and assign a float variable a particular value, and define a rank 0 tensor by applying any constant value, so that the rank 0 tensor has a single value filled in it. Then you can start printing it out, and and then you can see the outputs of how it works. So again, you do not have to worry about the code at all or any other aspects of programming I'm talking about. You're going to have the book, and you can practice all of your exercises, and you check the code in GitHub, and you can get all of that right now. Nothing to worry at all. If any particular concept or any particular point that I'm talking about is unclear, or you can certainly get that back when you take a deeper dive into the book, and you will be able to execute all the programs by yourself. And the purpose of this book is, again, to enable the fundamentals, as not like where a lot of other books will directly take you to some of the portions where it's going to get complicated to actually start implementing it. But the purpose of this book is to layer a greater foundation for you, so that you can actually be able to practice all the exercises, and you can come up with outcomes on each numerical operation or tensors or linear algebra and calculus, so that you will be able to practice it. But any person that's unclear, absolutely nothing to worry about. So again, a vector is contains a list of values. Unlike the rank 0 tensor, there's only going to be a single value in it, and the tensor can have a magnitude as well as direction as well. So let's take it as a x-axis and y-axis, and you also have a direction in which it is going to be. So for example, in this vector, we can have 3 and 9. So 3 is your x-axis and your 9 is on the y-axis. So graphically, you can represent it. And I mean, you can apply any Pythagorean theorem or any other theorems that you can apply, and you can execute it. So you can, this is an example I'm giving how to build a rank 1 tensor and how to produce an output for it. Again, rank 2 tensor is a rectangular array that can contain a number of elements, and that represent the second order tensors. And let's consider a matrix that contains the positive integers as x and y, where x and y belong to a set of n. And you can do a performance like matrix dot product, so where you're multiplying multiple matrices between x and y, and you can have x rows and y columns. And you can have for example, define any particular matrix like this, and then you can also determine what type of a rank of a tensor it is, and just print it out for your purpose. Just define some values and just print it out and see what type of a shape it has. It has like a 3x2 shape, or that will determine the type of tensor that you're going to have. Again, in this example, you can also shape the tensor. It's not necessarily like the type of tensor you're getting as an output is going to be how you want. You can shape it. So that shaping of a tensor is something you determine for each list, and we create a tensor rank to tensor. And in order to determine the number of elements in each of the nested lists, so we're going to create a tensor shape 3 and rank 2 tensor, and then we have a rank 2 with shape 3. Okay, so it is definitely possible to change and reshape a tensor in TensorFlow. So whatever the tensor value that you have initially defined, a rectangular tensor with a defined fixed values in it, you will be able to change it and reshape the tensor. So T of 1s is a great utility in TensorFlow that can allow you to create a tensor containing all the elements set to default the value of 1. So you can leverage that. So it's going to just default 1, 1, 1 instead of you manually passing the values. Or if you have a data set that you want to upload, then it comes with all the predefined values that you want to upload. But if you're going just for your practices purposes, for your foundational efforts of computing the max, you can go for this, and you can change the shape of a tensor and just default it by 1 with T of 1's function. And once you get it, you can shape the tensor and reshape it. So when we do this, we're getting the shape of the tensor looks like this. It looks like 1 to 4. And, you can now shape the tensor to actually be able to produce in a different way than what we are just displayed over there. That's your, what you call like a 1, 4, 2, and so we add a tensor here 1 to 4. Now I shape the tensor to your 1, 4, 2, 1, 8, and then I'm able to print it out in a different way altogether. See, all of your rows have been transformed into columns, and columns have been transformed into rows. So that's how we change and shape a tensor here. Okay, so again, as I mentioned, we can also do dot products with matrix multiplications, and in TensorFlow, in linear algebra, a matrix is a 2-dimensional array that contains a list of entries or arrays of entries with A by B. So let's define A with 504 matrix, and let's define B with a 4x5 matrix, and let's perform a calculation. If you're going to manually be able to do it, you're going to simply multiply 3 by 2, and then you're going to add up 9 by 1, and then you're going to add up 6 by 4, so on and so forth. But if you were to do it with TensorFlow, automatically all of this gets calculated, and you're going to get your output here. So so let's do this. We define a tensor here, and we just print it out, and we shape the rank of the tensor with the T of rank tensor, and that shows that this is a rank 2 tensor. And then again, let's declare another rank 2 tensor with a size 4 by 5, as we just seen over there. And then you just print the elements of the matrix and the shape, and then you perform a shape 4 by 5. So here automatically is going to perform all of this, and you're going to get a result matrix that comes with a dot product of A by B, which is a C. So that's how you can get all of this here. And again, the Moore Penrose pseudo inverse is a very popular in linear algebra. It has any matrix, and that comes up with either complex or real numbers, and it is unique. And a lot of companies leverage this for a singular value decomposition. And you can build a recommendation system. There's a YouTube video I created exclusively for Moore Penrose pseudo inverse. You can take a look at it to kind of break down these equations and see what it means, and how you can leverage it, and what is the meaning of it, and how it works, and what are the companies that are actually able to implement this. And again, you will have the code that you can write and you can execute it, and you can practice few exercises on your own to see how you can perform a Moore Penrose pseudo inverse for rank to tensor. And as I said, it's a direct application of singular value decomposition algorithm. And singular value decomposition is a Billion algorithm. The reason why we call it Billion algorithm is because a lot of companies leverage it. Amazon leverages it. Netflix will leverage it. So when you purchase a book on Amazon, you might be wondering, how am I able to get a recommendation of a similar book of the nature? Like, let's say you're trying to buy a book in PyTorch, and suddenly the next day morning when you check, it will tell you, okay, here is the latest PyTorch book on the bookshelf. This might be of interest to you, and we'll have similar chapters and content that you may be interested in. So how do they do it? So they do it with the singular value decomposition algorithm, which is primarily, applying with matrix X with agent vectors E, and you'll be able to perform this with a data matrix defined, and then you're going to define left singular vectors, and you're going to do a diagonal of singular values, and you're going to do a right singular vector. So this is how you do it, and here is your formula, and you can implement it. And I'll provide you more explanation on it. So in the interest of time, I'm going to be pacing up a little bit because we still have to get to the calculus portion of it. So you can again write a program, and you can prove that this is how the singular value decomposition algorithm works, and you'll be able to get the orthogonal transposed matrix V here. Okay, so that's how you work on it. So again, coming to calculus has a wholesale vital role in performing numerical computations in the supercomputing field. Many of the supercomputing field, like for example, if you want to calculate nuclear plasma turbulence, or you want to calculate aerodynamics, you leverage vector calculus, and you also leverage calculus for performing any numerical computations. So it has a process differentiation, which is actually a process in calculation. In calculus, leverage to find the derivative of a function. So you can perform any differentiation of function. The derivatives of the function can be represented with the Leibniz notation as differentiation of y by x is going to be a differentiation of f of x by dx, which is a Lagrange's notation of f of x or y. And again, you can define the derivative of a function, and you can represent it. And this is, as I said, is leveraged in many scientific and engineering fields for programming and scaling problems at scale. And differential calculus, in a nutshell, you can simply call calculus. How do you define it? It's simply nothing but a rate of change in a function at a particular point. So it's just a characterization of a derivative that signifies the rate of change in a function at a particular point. So there is a rate of function, for example, delta y, and to that the change in the independent variable, which is delta x. So in order to determine the change between the y and x, to compute the rate of change, is how you can leverage the calculus, and that's how this particular field of math has been introduced. And again, automatic differentiation is very important, especially if you are performing any Hamiltonian or Monte Carlo sampling statistics and mathematical applications for training the neural networks. And it is a chain rule based methodology for performing evaluation of derivatives of the functions, leveraging computer programs and libraries. Again, a lot of times for many decades, people have calculated the automatic differentiation manually by writing all of the equations on your own for performing in forward mode or performing in backward mode, all of the automatic differentiations. But again, that's no longer necessary. There's a lot of built-in modules that are coming up, like, for example, AutoGrad in your PyTorch. A number of other programming languages have introduced the automatic differentiation with a built-in library that you can leverage rather than actually going to be able to perform completely, from scratch. That you don't probably have to do that. So again, so as I mentioned here, so TensorFlow and PyTorch have the packages for AutoGrad, and you can perform. So here is a look at how you can do a forward differentiation, and you can do a backward differentiation of auto differentiation. And again, the way that you compute it, you can manually compute each of this, or you can actually run through the AutoGrad, and you can define it, and you can perform your calculations, and you can achieve your outcomes with that. Again, Jacobian matrix has a very vital and important role in calculus for matrix calculus. So let's take a look at why we're talking about Jacobi matrix here. So in 1835, Gustav Jacob Jacobi has invented this, and he has defined and invented the elliptical periodic functions, including the discovering fundamental properties of theta functions. And in 1836, he also introduced the Jacobi integral. And in 1841, he proposes Jacobian determinant from the partial derivatives and reintroduced the partial derivative Legendre notation. This is the symbol that he has introduced. And you can perform matrix calculus leveraging the Jacobian matrix. That's why they have a vital role in the field of mathematics. So a lot of applications you can compute and you can perform automatic differentiation leveraging Jacobian matrix as well. And here are a few computations on how you can perform it. And you can actually implement this in TensorFlow. So let's go to TensorFlow and see how we can leverage and implement automatic differentiation. We can do that with API called TF gradient tape. So TF dot gradient tape is a built-in function that comes in TensorFlow. For all of the gradients that you have in TensorFlow, you can compute them, and you can perform automatic differentiation based on the input variables that you pass. And so the reason why they define and call it as a tape is because you perform so many operations, numerical operations, forward differentiation or backward differentiation, numerical operations. The tape records each of these operations. So you can go back and rerun all of your particular steps that you executed on the gradient tape, and you can compute and read all the gradients associated with it. So you have a record history of every single operation you perform, and that's the advantage of leveraging the TF gradient tape API. And again, you can perform, for example, a simple gradient calculation with here, or you can perform an advanced calculation. It all depends on how you want to scale up your calculations. And again, here I'm declaring a TF gradient tape and with TF constant. And so I'm able to differentiate this and produce an outcome here. And the gradient has been computed to 10, and the gradient of 10 means the values of y are increasing at a rate of 10 units for every single unit of one increment in x. As I just explained about, it's all about the rate of change calculation here. The rate of, so for every gradient that was computed to 10, the gradient 10 means the values of y are changing at a rate of 10 units for every single unit, one increment in x. I mean, you can call increment or decrement, either way, it's a change. So you can call it a rate of change, in a nutshell for performing these computations. And again, the derivative of the first order function is a function itself, and a derivative of this function can be computed. And so not only the gradient tape API can operate on only scalars, but also it can perform any rank tensor scale as well. So I mean, this session usually requires a couple of hours for me to go through, but considering the time constraint, I'm gonna speed up a little bit, pace it up, so that just a couple of days ago I sent I shared on social media about chain rule, how we can leverage the chain rule in calculus, and we can perform the composite functions and that contains two or more functions. So you can take a look at the book and you can see how you can leverage the chain rule and how you can come up with your computations and how you can actually implement it in TensorFlow. So here, first, for every operation you're gonna perform in TensorFlow, I'll provide you a complete fundamentals of it, how it started and what is the purpose of it, and I will also provide you all the equations and formulas for you to go through and understand how you can derive this equation. And then I will introduce you to the program with a step-by-step mechanism of taking you to each input function and run through the TF gradient tape, and then you can do intermediate computations, and then you can actually print it out so you can see how you can perform chain rule. So, okay, here is the output of the chain rule, and so you can print it out and you can declare it, and you can multiply and verify the chain rule as well. And so let's take a look at back propagation. So back propagation, I'm going to explain in a way, there are a lot of built-in functions nowadays available for back propagation in TensorFlow and PyTorch, but I'm going to go old school on this. I'm going to actually tell you how to do a back propagation. If you were to compute it in Python, for example, how you are to do it. So as you just look at the inner workings of architecture stuff, the neural networks, deep neural networks, we just went about and we spoke about. And so here we're going to take a look at how do we do a back propagation of this. So every time you do weight computation, you have a very, you can have some error that occurs in your computation. So back propagation is something that you can leverage to rectify your issues, and you can come up with optimization of the weights. So initially we're going to initialize the weights so that we don't assign something constant, so that you're going to have bias in it. So we're going to initialize it, so that we're going to perform optimization by randomly initializing with filling any variables we're going to get, and then we're going to assign all these weights to it, and then we take a forward pass at it and we do the computation. So let's see, for each of this neuron, I've assigned few of the weights here, and and we do a weight computation here, and then we get the outputs determined. So we compute the net input. Let's say we compute the net input for y1 and y2. So how do we do it? So net input is basically, whatever the weight summation we perform, multiply that by each of the weight that we assign for the A1, and plus weight 2 multiplied by A2, plus we also introduce a couple of bias nodes here, which again we initialize with some weights associated to it, and we're going to multiply that with the bias node as well. That will give you the net input. So that is the net input. And let's also compute the net input for y2 as well, which is in the neural network here in the hidden layer. And then we're going to apply a logistic function as well. So as we spoke about sigmoid function, we also spoke about hypertangent function or tan function. You can also introduce a logistic function as well, or you can go for ReLU, which is a built-in function as well. So the logistic function, we're going to activate this leveraging a logistic function here. So when we do that, the net output here for A1, we're going to get actually as this computed here, and we're going to compute this as a net output here. Okay, so and then we do a net input for Z1. So that is the Z1 and Z2 here. So let's calculate that and see what we're going to get here. Z1, Z2, these are the values we have calculated. Similar to what we just saw, how we calculated Y1 and Y2. We're going to be similarly calculating the net input Z1 and Z2 as well. So this is the value you are able to get here. And, so this is the total weight summation we are calculating. And we're also taking the error into consideration for your, back propagation, so that you can compute the total error is basically the error that occurred in Z2 and the error that occurred in the Z1. So that's what we have here. So again, we compute the net input Z2. We also compute the Z2 here, and we also compute the net output Z2, and we apply the formula, and then, so we're going to produce the total error for the back propagation here, which is computed with this level. So you might be wondering, this is not really a lot of error that we're having for each feed-forward network when we are doing the weight summation or producing the output. But again, think about it think about reinforcement learning or any other mechanisms where you can apply this deep neural networks. You're going to be iteratively, episodically running this through multiple times. Sometimes it goes through millions of times. So that's when you run this back propagation, the error can be so minimized and rectified see a significant reduction in the error when you do this application episodically. So that's why it's very important that we reduce the back propagation, and we also reduce the vanishing and exploding gradients as well by leveraging the value function. But if you are leveraging like logistic function or sigmoid function or hypertangent function manually, then you will have to also take care of vanishing and exploding gradients as well. So in order to avoid it, try to leverage as much you can with like built-in program functions. But sometimes I go old school like this. For example, back propagation you can calculate like this, where you don't have to do it through a built-in function. Again, you can apply the chain rule for backward pass, and then you get the output for that, and that's the output. Yeah. So now let's see if you have any questions, and we'll try to answer those questions. Okay, here we are seeing some questions here, and so Sunil is asking a question. I have seen unsigned integer since learning C programming, but don't know when to use. What's the special use case of 64-bit unsigned integer? Okay. So primarily, whenever you want to utilize your unsigned integers, so when you have unsigned integer, you can have a positive or negative in both in it. So if you have a sign, you're going to have a particular direction for it. So whether you want to assign a positive or negative, but if you're going for an unsigned integer, you can assign both as well. But yes, it is there in the C. I have implemented in C, many decades ago. I implemented in C++ as well. So that concept still holds good, and it's still the same. But again, if you're going for larger scale operations, for example, you're going for like we talked about high performance computing applications, you want to calculate multi-algebraic grids where you want to calculate vector calculus, or you want to apply Navier-Stokes equations. Then the best way for you to be able to do that would be with floating pointers, because the vectors is something, again, we used to do it, leverage it back in the day then. But now when you're applying it, you might want to leverage floating pointers as well. The floating pointer is the best because it has the largest computation space available for your calculations, especially in the vector calculus for scientific applications and high performance computing. And also keep in mind, when you're doing high performance computing, it's just not the mathematical calculation you're producing it, because there are also other problems like serialization and parallelization. So when you're doing a serialization, let's say that we have a NASA computer, Palladius, that wants to perform a lot of computations. You want to count the number of stars in a galaxy. So if you're going to do serialization on a classic computer, it's going to run forever. You're going to probably take 1,000,000 years to get your output to say how many stars are there in a galaxy. But again, if you're going for parallelization, leveraging MPI, message passing interface, and you can also implement C++ and C programming languages in it for building your algorithm. So what it does is it's going to break down your algorithm, and each individual cluster is going to perform a numerical operation for each application, and it's going to produce, just like in your Apache Hadoop, your map reduce technique that performs each shuffle technique and map reduce technique on each particular cluster, and it's going to give you the output. So similarly, you can actually compute that in MPI, message passing interface, in C++, and that algorithm you can come with a parallelization. So let's say however many Palladius supercomputer has multiple clusters, and each of that you compute this application and produce an outcome, then we're going to assemble it, all of it. So whatever that serialization is doing to complete an application calculation, and it starts the next application, instead of that, you can combine all of your operations parallel. You perform all of your calculations, then you produce outcomes already, and just assemble it. You have in few minutes the answer of how many stars are in a galaxy. I mean, whether it's a stars in galaxy, or you want to compute the nuclear plasma turbulence, how you produce a nuclear fission, how you do a nuclear fusion, and all of these applications you can compute in with high performance computing. Especially for a nuclear fusion, what we are doing is we are trying to harvest the energy that sun is providing, and we are trying to reproduce by ourselves through the plasma turbulence. So again, I have covered these applications on high performance computing, what companies have implemented it, how we can implement it, what are the libraries we need to leverage, how we can compute all of that, you can find in the upcoming book as well. Anyway, thanks for asking the question though. If you do have any other questions, please feel free to ask at this time and I can clarify for you. Any other questions? Any other questions, please? Please go ahead and raise up your question on any of the topics that we have covered, or any other questions on any other. I mean, it doesn't matter as long as it's data science and machine learning and deep learning. Please feel free to come up with any questions that you may have. Okay, if there are no further questions, and you can also send the questions later, either to me or you can also send to the host of the particular, this conference, and I will respond to you for any open questions you may have later as well. And again, I would like to extend my thanks, for inviting me here, and I would like to thank the host for having this opportunity for me to present this as well. Thank you very much, and there are no further questions, then I will hand it from my side back to the host now. Hello. What is the best resources for learning the TensorFlow? Okay, so actually the best thing is like TensorFlow.org has provided a various number of TensorFlow applications on natural language processing, and they also have provided various applications on different regular techniques that we can implement through TensorFlow. All of that you can find from official TensorFlow.org. And also, like, there are a lot of GitHub repositories that you can go through, which I'll be sharing frequently, on many applications like LinkedIn, at various social media platforms. I keep sharing this information, so you can certainly take a look at that, and you can find the resources for TensorFlow as well. And you will be able to take a deeper dive into it and start implementing it, and you can discover more applications. But again, I would certainly say also my book would be a best foundational course for TensorFlow, because I started from scratch in terms of how we go about linear algebra and calculus as well, and and also a few other applications. So certainly you'll be able to leverage that as well. But again, if you're officially going to TensorFlow.org, then that would be the best place for you to go and take a look at that, and you can start exploring TensorFlow. A lot of tutorials are available that you can definitely take advantage of, and you can certainly leverage that for your purposes. Again, similarly, PyTorch also has pytorch.org, and you can find some samples there. And also, please always look at my LinkedIn articles that I share, where I if there are more common algorithms that are leveraged, and for each of the algorithms like naive Bayes or clustering or classification or regression or any other algorithm on TensorFlow, PyTorch, Python, or R, I keep sharing it on LinkedIn very regularly. Please take a look at the post I share on LinkedIn, and you'll find a lot of information on all of these resources. And if you check that on a daily basis, you will actually find more information there as well. So yeah, please take a look at that, and you will find all of that. But for now, you can get started with TensorFlow.org. And thanks very much again for this question. And if you do have any other questions, please do not hesitate to bring it up now.